Imagine for a moment you gazing at the night sky and spot the closest star to our sun, Proxima Centauri. It's only 4.2 light years away. Only, I said. Do you know what that means? If we could travel at the speed of a commercial jet, it would take us over 5 million years to get there. And if we used the fastest probe ever built by humanity, the Parker Solar Probe, we'd still need 6,300 years to complete that journey. Now, tell me, can we really leave our solar system and explore other worlds? That's the question we're going to answer today. We're diving into the incredible physical difficulties that make interstellar travel humanity's greatest technological challenge. But we're also going to uncover the most fascinating solutions scientists around the world are developing. From solar sails to fusion engines, from wormholes to real-world projects like Breakthrough Starshot, you'll discover that science fiction might be closer to reality than you imagine. Hey there, cosmic explorers. Welcome to Cosmic Frontiers, where we transform the mysteries of the universe into accessible knowledge. We're on an incredible journey together towards our first 1,000 subscribers, and each one of you is a fundamental part of this community that's growing every single day. To understand why interstellar travel is so challenging, we first need to grasp the absolutely incomprehensible scale of space. When we talk about interstellar distances, our brains simply can't process the numbers involved. Let's start with an analogy that will make you understand the size of the problem. Imagine the sun is the size of a soccer ball here on Earth. On that scale, Earth would be a grain of sand, 26 meters away. Pluto would be another grain of sand, 1 kilometer away. Now, where do you think Proxima Centauri, our nearest neighboring star, would be? It would be 6,700 kilometers away. It's like the sun is a soccer ball in Rio de Janeiro, and the nearest star is another soccer ball in Moscow. This distance represents 40 trillion kilometers in the real world. To give you an idea, if we could build a bridge to Proxima Centauri, it would wrap around the Earth 267 million times. Light, the fastest thing we know in the universe, takes 4 years and 3 months to make that trip. But distance is just the first of our problems. Let's talk about energy. To accelerate a spacecraft to a significant speed, say 10% of the speed of light, we would need an amount of energy that would give any engineer nightmares. According to calculations by physicists like Robert Forward and Freeman Dyson, to accelerate a spacecraft of just 1 ton to 10% of the speed of light, we would need energy equivalent to the world's electricity consumption for 2 entire years. And that is just to accelerate. Do we forget we also need to decelerate when we reach our destination? Einstein teaches us through his theory of relativity that as we approach the speed of light, an object's mass increases dramatically, requiring more and more energy to keep accelerating. It's like trying to push a car uphill, but as you go up, the car gets heavier and heavier. At the speed of light, mass would become infinite, which would require infinite energy, a physical impossibility. Now let's add another lethal ingredient to our recipe of challenges: cosmic radiation. Interstellar space isn't a perfect vacuum. It's filled with high-energy particles, electromagnetic radiation, and even scattered hydrogen atoms. It might not seem like much, but when you're traveling at a significant fraction of the speed of light, these atoms become devastating projectiles. A single hydrogen atom, hitting a spacecraft at 10% of the speed of light, would have the energy of a rifle bullet. Imagine millions of these atomic projectiles constantly bombarding the spacecraft. It's like trying to cross a cosmic hailstorm, where each ice pellet has the energy of a bullet. The shielding needed to protect both the spacecraft and its occupants would be so massive that it would make the mission even more impossible from an energetic standpoint. Scientists like the Portuguese physicist Luís Y. calculated that a spacecraft traveling at 20% of the speed of light would need shielding at least 1 meter thick made of ultra-resistant material. This would add tens of tons to the spacecraft's mass, exponentially multiplying the energy requirements. But this is where the story gets fascinating. Cosmic explorers, faced with these seemingly impossible challenges, the human mind did what it always does. It sought creative solutions, and some of them are so elegant they seem like magic. The first revolutionary solution is the solar sail, a concept that transforms light itself into propulsion. The idea, first proposed by Russian physicist Konstantin Tsiolkovsky in 1924, is simple and ingenious. Just as wind pushes a boat's sail, the pressure of solar radiation can push an ultra-thin space sail. The Lord's light exerts a tiny but constant pressure. It's like a cosmic breeze that never stops blowing. A solar sail would be made of ultralight, reflective material, perhaps just a few atoms thick, but covering an enormous area. Imagine a sheet of aluminum foil the size of several soccer fields, but millions of times thinner. Japanese physicist Yuji Ikeda demonstrated that a 1 square kilometer solar sail, weighing only a few kilograms, could gradually accelerate a small probe to speeds of 20% of the speed of light. The secret lies in constant acceleration. Even if it's a small force, applied continuously for years, it can result in impressive speeds. It's like the difference between a strong, quick push and a weak but constant push for hours. But solar sails have limitations. Once the spacecraft moves away from the sun, the radiation pressure drops drastically. That's where the revolutionary concept of laser-driven solar sails comes in, an idea that's becoming a reality through projects like Breakthrough Starshot. Imagine billions of lasers on Earth, perfectly synchronized, creating a beam of light so powerful it could propel a space sail far beyond the solar system. Physicist Philip Lubin from the University of California calculated that a laser system with 100 gigawatts of power could accelerate small probes to 20% of the speed of light in just a few minutes. Can you imagine? Instead of thousands of years, these minicrafts would reach Proxima Centauri in just 20 years. It's the difference between a journey that would last hundreds of human generations and one that a person could see begin in youth and end in maturity. But let us go beyond solar sails and explore the holy grail of space propulsion. Nuclear fusion engines. Here we're talking about the same reaction that powers the sun and all the stars in the universe. Nuclear fusion releases monumental amounts of energy, far more than any chemical fuel could ever dream of producing. A fusion engine would work by capturing the energy released when hydrogen nuclei fuse to form helium, exactly as happens in the heart of the sun. Physicist Robert Bussard proposed an ingenious concept called the Bussard ramjet, a spacecraft that would collect hydrogen from interstellar space itself to fuel its fusion engines. Imagine a spacecraft with a gigantic magnetic funnel at the front, collecting hydrogen atoms from space, like a whale collects plankton from the ocean. This hydrogen would then be compressed and heated to temperatures of 100 million degrees Celsius, initiating the fusion reaction. The resulting energy would be directed backward, propelling the spacecraft forward. The concept is so elegant that Carl Sagan commented, "It's like building a ship that feeds itself during the journey." The advantage is obvious. We don't need to carry fuel because space itself provides the food for the engines. But, as always happens in physics, reality is more complicated than theory. Physicist John Martin discovered that to collect enough hydrogen, the magnetic funnel would need to be hundreds of kilometers in diameter. Furthermore, the density of hydrogen in interstellar space is so low that it would be like trying to feed yourself by collecting crumbs scattered across a soccer field. Still, modified versions of fusion engines continue to be one of our best hopes for interstellar travel. Projects like the one being developed by NASA in partnership with the University of Washington showed that we might be closer to controlled fusion than we imagined. Now let's enter the territory of more exotic physics, nuclear pulse propulsion, and space-time manipulation concepts. Project Orion, conceived in the 1950s by physicists like Freeman Dyson and Ted Taylor, proposed something that sounded completely insane: a spacecraft propelled by nuclear explosions. The idea was to detonate small nuclear bombs behind the spacecraft, using the explosion to push it forward. It's like tying dynamite to the back of a car and using the explosions to accelerate. Except we're talking about nuclear energy and relativistic speeds. Calculations showed that this approach could, theoretically, accelerate a spacecraft to 5% of the speed of light. A trip to Proxima Centauri would take only 85 years. Physicist Freeman Dyson even calculated that an Orion spacecraft, the size of a skyscraper, could carry an entire city to the stars. But here we encounter not only technical challenges, but also deeply ethical and practical issues. We're talking about detonating thousands of nuclear weapons in space. Besides the obvious risks, there's the Partial Nuclear Test Ban Treaty, which prohibits nuclear explosions in space. And then we come to the most fascinating and controversial concept of all. These hypothetical space-time structures were predicted by Einstein's theory of general relativity and would, in theory, offer shortcuts through the universe. Imagine space as a sheet of paper. Normally, to go from one point to another, we'd have to travel across the surface of the sheet. But what if we could fold the sheet and make a hole that directly connected to distant points? That would be a wormhole, a tunnel through the very fabric of spacetime. Physicist Kip Thorne, Nobel laureate and scientific consultant for the movie Interstellar, mathematically demonstrated that wormholes are theoretically possible. They could allow instantaneous travel between points separated by thousands of light years. But, and this is a gigantic but, creating or keeping a wormhole open would require something called exotic matter with negative energy density. This is a form of matter that has never been observed and may not even exist. It's like trying to build a bridge using a material that might be impossible to manufacture. Furthermore, even if natural wormholes exist in the universe, they would be extremely unstable. Physicist Stephen Hawking showed that anything entering a wormhole, including the very light that would allow us to see it, would cause its instant collapse. But don't lose hope, cosmic explorers. While we discuss these fascinating theories, there are real projects happening right now that are taking the first concrete steps towards the stars. The most ambitious and realistic project currently is Breakthrough Starshot, funded by Russian billionaire Yuri Milner and supported by scientists like Stephen Hawking. This project aims to send thousands of mini-probes, each the size of a smartphone, to Proxima Centauri, using the laser-driven solar sail technology we mentioned earlier. These nanocrafts would be accelerated to 20% of the speed of light by an array of Earth-based lasers. Each probe would weigh only a few grams and carry miniaturized cameras, sensors, and communication equipment. The idea is that some of these probes will survive the 20-year journey and send back the first images of another star system. The project faces monumental technical challenges. How do you build electronic equipment that works after 20 years in interstellar space? How do you get these mini-probes to communicate with us from 4 light-years away? How do you ensure they aren't destroyed by dust particles during acceleration? But the most impressive thing is that these aren't impossible theoretical problems. They are complex, but solvable engineering challenges. The difference is crucial. We're talking about technology that can be developed in the coming decades, not in hypothetical future centuries. Harvard physicist Avi Loeb, one of the project leaders, is optimistic. For the first time in human history, we have the technology needed to take the first real steps towards the stars. It's no longer science fiction, it's feasible science. Other fascinating projects are being developed in parallel. NASA is investigating concepts of human hibernation for long-duration voyages. Engineers are designing sustaining habitats that could house generations of explorers on multi-generational interstellar spacecraft. The Japanese company JAXA is developing increasingly sophisticated solar sails, testing materials and navigation techniques. ESA, the European Space Agency, is studying ion engines that, although slow, could operate continuously for decades. Even seemingly impossible concepts like warp drives, popularized by Star Trek, are receiving serious scientific attention. Physicist Miguel Alcubierre showed that, mathematically, it would be possible to warp space around a spacecraft, allowing faster-than-light travel without violating relativity. The concept works by contracting space in front of the spacecraft and expanding it behind. The spacecraft wouldn't move through space, but would surf on a wave of distorted spacetime. Unfortunately, this would also require impossible amounts of exotic energy, but at least it shows us that the universe might have loopholes we haven't discovered yet. We've reached the end of this cosmic journey with 3 revelations that should stick in your minds. First, interstellar travel is the most complex technological challenge humanity has ever faced, requiring revolutionary advancements in physics, engineering, and even biology. Second, despite monumental obstacles, we have scientifically sound concepts that could take us to the stars, from solar sails to fusion engines. And third, projects like Breakthrough Starshot prove that we're no longer just dreaming, we're building. But here's the deeper reflection. Cosmic explorers, perhaps the question isn't just can we leave the solar system, but rather should we? Every technology we develop for interstellar travel, nuclear fusion, advanced artificial intelligence, life support systems, also transforms our lives here on Earth. By seeking the stars, we discover more about ourselves. Carl Sagan once said, "Space exploration leads directly to the concept that Earth is a pale blue dot, insignificant on a cosmic scale, but incredibly precious as the only home we know." Perhaps our journey towards the stars is paradoxically a journey back home, a rediscovery of the unique value and fragility of our home planet. Now I want to hear from you, cosmic explorers. In the comments, tell me, if you could choose just one interstellar travel technology to invest all of humanity's scientific research into, which would it be? Solar sails, fusion engines, nuclear propulsion, or some exotic technology like wormholes? And justify your choice. I want to see the reasoning behind your decisions. We're on an amazing journey towards 1,000 cosmic explorers. If this video expanded your horizons on the possibilities of interstellar travel, join our crew by clicking subscribe. Every new member strengthens our community of universe enthusiasts. Like this video if it made you dream of the stars, and share it with someone else who is also fascinated by the limits of science and space exploration. And don't forget, cosmic explorers, what mystery of the universe do you want me to talk about in the next video? Leave your suggestions in the comments. I want to know what cosmic frontiers you want to explore together. In the next video, we'll dive into another fascinating enigma: supermassive black holes and how they might have shaped the formation of entire galaxies. Until then, keep looking at the stars and questioning the limits of what's possible.